Okay, so we're going to try and integrate this integral here, 1 over cotangent of x plus sine of x with respect to x over this interval pi over 2 to pi over 6. Now, just got to be careful with this cotangent of x. So we know that cotangent of x is cosine of x over sine of x. So this sine value, we've got to be careful. We don't want a 0 in here because this could render this integral as non-continuous and could give us a false answer. So over this range here, pi over 6, sine of pi over 6, that's fine, that's a half. And pi over 2, sine of pi over 2 we know is 1. So that's safe. So we know we're in here with an undefined value for cotangent. So that's fine. So that's, now let's have a look at what's in the integrand. So 1 over cotangent x plus sine of x. Now let's see if we can do something with this. There's no point trying to integrate that or use sub straight off. I don't think there's anything that's going to work. So let's do some trig and algebra on that. So cotangent of x plus sine of x. Let's just rewrite that as its identity. Cosine of x over sine of x plus sine of x. Now if we could turn this into one fraction, that would be a good start. So we just multiply both sides by sine of x. So multiply the sine of x by sine of x over sine of x, which is just 1. So then we're going to get cosine of x plus sine squared of x. And then the whole thing can be over sine of x. So now this is looking a little bit more promising. So sine squared of x. Now if we could make this in terms of cosine, that would be good. Now we know there's a trig identity, one of the first ones we ever learned. We've got that one. So we can make that in terms of sine squared and get our cosine in there. So then we've got sine squared of x, 1 minus cosine squared of x. Okay, let's plug that in there. So then we've got cosine of x plus 1 minus cosine squared of x. And then that's all over sine of x. So now this is looking good for some sort of u substitution there. We've got a couple of cosine terms and a sine term in our denominators where we want it. So now let's rewrite this integral in terms of this. So, okay, so now we've got pi over 2 to pi over 6 and then 1 over, then we put this one in our denominator. So cosine of x plus 1 minus cosine squared of x all over sine of x dx still. Okay, now we can bring this sign up to the top. That's fine, so let's just do that. Just neaten things up. So that would take care of that. And then we're looking like we could just go for a u substitution here and then see what we can do from there. So sensible u substitution here would be, I wouldn't say the sine of x, because then we've got to try and cancel all these out from one derivative of sine of x. That's not going to work. So if we let u equal cosine of x, we'll get a derivative that involves sine of x, and then we can perhaps cancel this out. So let's try that. So u equals cosine of x. So normal rules when we're doing u substitution, take the derivative, we've got negative sine of x dx. And now I always like to isolate my dx so I know what I'm plugging in. So now I'll have dx equals negative du over sine of x. So we can do that. But as we've got a definite integral, I like to change my parameters of my integration as we go along rather than do a big backward substitution. So let's go for this one. So the upper bound equals, well, u equals cosine of x. So u1 will be cosine of pi over 2. So that we know. So that is just 0. And then our bottom one, our lower bound, u2 will be cosine of pi over 6 Well, we know that from the unit circle, that is root 3 over 2. So I've got all the tools I need now to take this into our u variable. So, parameters of integration, cosine pi over 2, that's 0. And then cosine pi over 6 is root 3 over 2. So that takes care of that. Sine of x I'm just going to put in now, just so as we can see what happens to it. And then cosine of x is just u. So I've got a u plus 1 minus, and then cosine squared would just be u squared. And then my dx, I've got negative du over sine x. So negative du over sine of x. And then one of my favourite bits I like to do, just cancel those out. Okay, so now I've got u plus 1 minus u squared. So looking ahead, and with this minus sign here, maybe I want to distribute this minus sign through this, and then we can cancel out this minus sign. So why don't we just multiply all these terms by minus 1, and then we get the reciprocal, that's the negative of that, and then we can cancel that out. So let's just do that. So that's going to make our life a lot easier. So now we're going to have a 1 over, so distribute this minus 1 through here. So minus u squared becomes u squared, plus u becomes negative u, plus 1, negative 1. And then just straight into du. Okay, now got to try and do something with this now. So I can't seem to factor that. Quadratic formula doesn't look like it's going to be really helpful just yet, so I'm going to complete the square. That's probably a good way to do that. And then maybe we could pick up some trig identity or some integral identity to help us with that. So let's go from 0 to root 3 over 2. Keep our 1. Okay, u squared minus u minus 1. Complete the square of that. I think we can do that in our head. So we've got a u minus half of that coefficient there, and then square it. So now we've gained an extra 1/4, which we now need to substitute off. So foiling that out, with just this terms here, we've gained 1/4. So now let's just substitute that off. So minus 1/4 minus 1 minus 5 over 4. And that's still du. Okay, right, let's just clear this stuff off the board and let's work out what we're going to do with all of this. Okay, so we've got this here. Now it's looking like we might be able to find our inverse tangent if we integrate. So we know that if we integrate 1 over x squared plus 1 dx, we know that this is the inverse tangent. So we could be looking for something like that, but our minus sign is getting in our way, and this u minus 1/2 is getting in the way. So let's just do another u substitution and get rid of this u minus 1/2. That's going to be a good start. So let's find another letter. So v I don't like because it looks like a u, so I'm going to go for w. So w equals u minus 1/2. Now this is nice and easy to differentiate. So dw is just du. So that's straightforward. And then our parameters now, we've got 0 and root 3 over 2. So if w equals u minus 1/2, we just need to subtract 1/2 from all of these. So w1 is 0 minus 1/2, and w2 is going to root 3 over 2 minus 1/2. Okay, well these can all be very easily simplified. That just becomes minus 1/2, and that just becomes root 3 minus 1 over 2, common denominators. Okay, right, let's take this off the board and put this integral up here, and we'll try and find this in terms of our w. Okay, let's take this into our variable w. So now our parameters, w1 is minus 1/2, and w2 is positive root 3 minus 1 over 2. So that's our parameters. And then this, take this into w, which is straightforward. That just becomes w, and du just becomes dw. So now we've got 1 over w squared minus 5 over 4 dw. Okay, right, still looking a little bit awkward. We've got w squared minus 5 over 4. Now that our integral identity is a +1 or -1 when we've got our w squared. So let's do something with this constant here, minus 5 over 4. If we multiply all these terms by minus 4 over 5, that will then give us a +1. So let's try that. So minus a half, √3 minus 1 over 2. Okay, everything multiplied by minus 4 over 5. So that just gives us that. And then we have minus 4/5 w squared. And then multiply that by 4 over 5. So just write that in there like this. You'll see that this just becomes 1. So when you've got minus times another minus, +1. Okay, and then we're still dw. Okay, now there's another identity here appearing actually, which could be quite good. We've got minus 4/5, which can come out front. Let's not worry about that. But this, we could be looking at our hyperbolic tangent when we integrate. So we know that if we do the integral of 1 over 1 minus x squared dx, this could give us the hyperbolic tangent with respect to x. So we could do that. So let's try our values for that. So that would involve switching this round and bringing this constant out the front. So let's do that. So minus 4 over 5, that's just bringing this constant out, that's fully legitimate. Minus a half, √3 minus 1 over 2. So now this now becomes a 1. And then we've got 1 minus 4/5 w squared. Okay. So dw. So we're still not quite there, still looking a bit awkward to look something a little bit like this. So let's just try one more substitution to get this 4/5 w squared into another letter squared. And then let's see what happens there. So let's pick another letter. So X, Y and Z I don't like using. So let's go the other way down the alphabet. Let's pick a T. So let T equal 4/5 w squared. Okay, now here, if we pick this substitution, we'll make life awkward for ourselves, because when we take the derivative of this, we're going to end up with 2w times 4/5. And that's going to make things very awkward here. You're going to end up with a row w at the top there. So why don't we take another approach and let t squared equal 4/5 w squared. And then we've got exactly our 1 minus t squared in our integrand. But we can't just go straight into the t. We need to take the derivative and all the other things that we need to do and change these parameters. So let's take the square root of both sides. So t equals 2 over square root of 5w. Now we've got something we can work with, because now we've got dt is just 2 over √5 dw. So that's good. So now getting dw on its own. So dw equals √5 over 2 dt. That's great. That's going to be working really well for us in here, changing this. But now our parameters. So our upper bound, all we have to do now, as our t equals 2 over √5w, just multiply all these by 2 √5. So we've got minus a half times 2 over √5. Okay, well we can simplify that up a little bit. They cancel out and we're left with minus 1 over square root of 5. And then t2, let's have a look at that one. So we've got √3 minus 1 over 2. So that 2 and this 2 is going to put us in a good place. So 2 over √5. So then these cancel out, and then we get an ugly looking root 3 minus 1 over root 5. So that's our parameters. So let's take this integrand now into the t world. So I'm going to write this up the top and then go from there. Okay, so now let's take this into our variable t. So dw for dt, that will be root 5 over 2. The 4/5 w squared, that will just become t squared. And then our parameters are here, and then we've got this constant multiple here. So we've got minus 4/5. So minus 1 over root 5. And then root 3 minus 1 over root 5. Okay. And then 1 over 1 minus t squared. So then we're looking like we go straight into our integration, and our dw becomes this one, root 5 over 2. So I'm just going to write that over there like that for now. So this is a constant multiple which I could have stuck on here. So now I could take this out of the integrand and multiply this by this, and then we just get a straightforward integrand. So minus 4/5 times root 5 over 2. Okay, well, these will cancel out to give us a minus 2, and that's a 1. And then if we divide both of these by root 5, we just end up with root 5, and that would just become 1. So then we end up with minus 2 over root 5. Okay, that's great. So that's good in there. So now, let's just take this off here. We don't need that working now. So we've got minus 1 over root 5. And root 3 minus 1 over root 5. And then 1 minus t squared in our denominator, and dt. Okay, right. So we're ready finally to integrate. So let's go for that. So minus 2 over root 5. So take this up here. So minus 2 over square root of 5. And then straight into integration. Hyperbolic tangent of t. And then we evaluate this over our parameters. So minus 1 over square root of 5, and root 3 minus 1 over root 5. Okay, so let's work that out. So now we've got, actually I'm going to take this off the board, give us a bit more space. We don't need this bit here now. I want this bit here to write my answer in. So now this is going to be minus 2 over square root of 5. Let's take this bit off as well. We've done that bit. And then we've got hyperbolic tangent of minus 1 over root 5. And then we're going to subtract the hyperbolic tangent of root 3 minus 1 over root 5. And then more brackets in there. Okay, now let's get the calculator out and see what we get for this. So we've got minus 2 over square root of 5. Okay, so now after plugging all these values in the calculator, this one here becomes to 5 decimal places, 0.48121. And then we subtract this one here, which was 0.33989, also to 5 decimal places. So that, now simplify that off. We've got minus 2 over square root of 5 times minus 0.82110. And if you plug that into your calculator to 5 decimal places, you'll get positive 0.73442. And that gives us the answer to our integral 5 finally. So 0.73442. That's 5 decimal places. Okay.